Alright, it's time for the solutions for the Mastery Quiz 15 review. So unless I'm taking a little bit different approach, I'm going to have the answers already there. And then I'm just going to explain where I got them from. Because there is a lot that you just put in the calculator, a lot of me writing stuff, and it makes it just a shorter video, and makes it easier to get through all these. So the first thing you can do is fill in this table here. You have to remember that all the rows add up to the total there on the right. So 14 plus something has to equal 24. Well, that number has to be 10. And if you have this being 10, you know that 3 plus something has to equal 10. So there's a 7 that goes in there. And 6 plus 7 gives you 13. And 13 plus something has to equal 24. That number is 11. And if you have 11, 3 plus something is going to equal 11, and that number's got to be 8. So there is just filling out those numbers there. These next part, you got to get joint relative frequencies, and you got to get marginal relative frequencies. On these, anytime you have a joint relative or marginal relative, you're going to divide by the grand total, which is the 24 right there. So just by default, you divide by the grand total, and then you just have to figure out what number goes on top. And that's where you actually read the problem. So joint relative frequency of playing a sport and not playing an instrument. Here are all the playing sport things, not playing an instrument right there. Well, that's number 7, so 7 goes up top. 7 divided by 24 and round it to the second decimal place gives you 29%. Just round the whole percent amount there. Next one, joint relative frequency of playing an instrument and not playing a sport. So plays an instrument, doesn't play a sport, that would be 8 right there. And then on to the marginal relative frequencies. On these ones, it gives you just a group. Plays an instrument. Well, if you play an instrument, you're in this column, and the total for that, there are 14 of them. And so that's where the 14 and the 24 comes from. The next one is marginal relative frequency of playing a sport. You figure out how many people play a sport. There are 13 of them, so that's where the 13 over the 24 comes from. That brings us over to the right side. 6, 7, and 8. On 6, because a person plays a sport, what is the conditional? Given a person plays a sport. So you're given this row here. Was a conditional probability of playing an instrument. Plays an instrument. So the given part tells you the total you're going to use. That's the 13 there. And the plays an instrument lets you point at the 6 people there. So that's why it's 6 over the 13. On number 7, conditional probability of playing an instrument, given the person does not play a sport. So does not play a sport is this row. That's a total of 11. And probability of playing an instrument, there are 8 of them that play an instrument but don't play a sport. So it's 8 out of 11, gives you 73%. So it gives you that. Does the data suggest there is a correlation between playing a sport and playing an instrument? Explain. I would say no on this one. If you look at these joint frequencies here, you'll see that, actually, if you just look at all of them here, they're actually fairly evenly distributed here. The only part that's not similar, so these are really similar numbers, is not doing either of them. And that would only suggest that more people play an instrument or play a sport, or both, than don't. And yeah, if you look at how many people play an instrument and how many don't, look at how many play sport and how many don't, it's fairly evenly distributed, so it's not these. If you were to get these joint relative frequencies for all of them, it'd be pretty close to the same, except for the 3 there. But yeah, one does not suggest that you do the other thing. So playing a sport doesn't mean you're going to play an instrument, or playing a sport doesn't mean that you don't play an instrument, or anything like that. Next section. So on 9, you need to plot your scatter plot, and that's these red dots over here. You just got to remember that these are the x's. X is there. The y's are the next row. So you got the point 12, 47, you know, where that point comes in, and so on and so forth. And then use a calculator to get line best fit. You plug in a calculator, make sure you do the Lin reg ax plus b thing, and you'll get this equation here. And hopefully your calculator is already set up to get the correlation coefficient while you're at it, even though we're not getting on this one. 11, you need to sketch the graph of this. To sketch this line, look at the y-intercept. You have 22.45, that's about there. So I drew it in blue for your reference. you're going to start there. You just put a point there right on your y-axis, so you have a starting point. The slope is the number in front of x. That has a slope of 1.22, and so we're going to go up 1.22 as we go right 1, but right here that doesn't count by 1s, it counts by 5s. So if you're going to go right 5, you actually have to go up about 6. And so if you go right 5 and up 6, you'll get a point about there, and after you have that, you can connect your line, and you'll be good to go. Visually, is this line a good fit for the data? I would say yes, because it's going pretty close through the center of the data. You have about the same amount above as you do below. A little bit of, I think I just didn't do my slope correct. I probably should have done a little bit more shallow. But yeah, it's a fairly good fit for the data because it's close. It goes through the middle of the points. It's about the same above and below and whatnot. 13. Use the line of best fit to predict the average longevity if the maximum longevity is 6 years. So what you're going to do is you're going to take this equation, and you're going to take this 6 and you're going to plug it in. But you don't plug it into the x, you're going to plug it into the y, because this is a maximum longevity, and maximum longevity is a y value. And so the 6 goes in for y. That's where I got this equation from. And you don't know x, so you have to figure out x at this point. So this is drawing on your solving equations knowledge. You need to subtract the 22.45 from both sides, and that's going to give you a negative number on the left, which is okay. And then you need to get rid of the number that's in front of the x, so we're going to divide both sides by 1.22, and when you do that, you're going to get 13.48 there, and your x value is going to be about that. And then brings us to 14. On 14, the line best fit to predict the maximum longevity if the average is 52. So this average 52 is an x value. So I can take the 52 and plug it into my equation in for the x spot this time instead of the y. So that's why I got this parenthesis 52 there, because I put 52 in for the x. When you compute that and you add things up, you'll get 85.89, and that's it. 15. You need to explain what the y-intercept stands for and what the slope stands for in this situation. I didn't write it all out because, well, I just don't want to bore you with a bunch of writing. But the y-intercept is this 22.45. That stands for the maximum longevity given the average is 0. So you think about your y-intercept is the y value when x is 0. Fill those y's and x's with actually what they stand for. So it's the maximum longevity if the average longevity is 0. So that's what the y-intercept means. The slope means, right here, well, this is the slope 1.22. That means that your y goes up that much for each x going up 1. In other words, your maximum longevity goes up 1.22 each time your average longevity goes up 1 year. And that's what your slope stands for. And that brings us to our next section here. Again, you're going to plug in this data set. The first row is going to stand for the x's. The second row stands for the y's. Make sure you do L1 for your x's, L2 for your y's. And you get your line of best fit, which is this guy here. The correlation coefficient also shows up on that. It's 0.99. You need to round to the second decimal place, but don't round up to 1 on correlation coefficient. Describe the correlation. This is a very strong positive correlation. 0.99 is about as strong as you can get, except for being actually 1, which is almost impossible with real data. Brings us to 19. What does the slope and y-intercept mean in the context of this situation? So we just talked about that on the previous slide. But this is my y-intercept. And this is a y value, which is per capita consumption of whole milk. And you get this y value when x is 0. So if there were no marriages in Virginia, as in your marriage rate was 0, then this is be your expected per capita consumption of milk, which kind of doesn't make sense, because that'd be everyone giving up 1.47 gallons of milk. Which doesn't make sense, but that's what it is. The slope, on the other hand, 1.03, that just stands for each time your marriage rate goes up 1, your your per capita consumption of whole milk would go up 1.03 gallons. And so they're just fairly similar to each other. If one goes up 1, the other one goes up 1.03. And that's what your slope stands for. 20, is this a causational relationship? No. Never, ever, 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 ever do you say that if you only have a correlation, which is all that we have. The only way you get causational is if you actually run a controlled experiment, a control group, an experimental group, and all of that. This is just a correlation. Correlation is not the same thing as causation. The answer is no. 21. Let's stop. Let's do 21 quick. So use the line best fit to predict the marriage rate in Virginia. The per capita consumption is 10.6 gallons. Well, this is a y value again, and so I'm rewriting this equation, except I'm replacing the y with 10.6. I get this guy. I need to get x by itself, so I'm going to add 1.47, because I'm trying to get things away from the x, to both sides. That'll give you 12.07, and on the right side you got this thing with the x still, you got to get rid of it. So divide both sides by 1.03, and if you do 12.07 divided by 1.03, you get x equals 11.72, and that's done. And yeah, I'm going to do it all in one video. Number 22. You need to compute the predicted values and residuals in the model, giving you your best fit. So here's my line of best fit. If you want to get these predicted values, you take the you take the x value, -1, and you come over here and you put it in for x. 11 times -1, and then you add 8. That'll give you a -3. So that's my predicted value. And you just keep going down, plug in 4. 4 times 11 is 44, plus 8 gives you 52. And then the next one, plug in 8, you get 88, plus 8 gives you 96. And then you subtract. Once you have the predicted values, you need to subtract them from the actual y values, and you get these numbers, which are called the residuals. You can just subtract them right across. -11 minus -3 gives you -7, and so on down the row. And the same thing down here. We're actually going to use the exact same formula there. You plug in -3, 2, and 0 in for x, and then add 8 to it, and you'll get these predicted values. You then subtract them from the actual values, and you get these residuals here of 1, 0, and then, oh, this should be -1. Sorry, my bad. Sorry, I messed up there. I messed up on this predicted value. It's -25, which way you say. Anyway, you get 2 for your residual for that. And that brings us to answering all these questions about stuff. So, 23, based off the residuals, which data sets is the model most appropriate? Oh, sorry, I should say which data set. Explain why that data set and not the other. So, something to tell if something's more appropriate than the other is you want your residuals to be small. Here we have much smaller residuals than for this guy, and so this model works best for the second data set, much better than the first one, because the first one has fairly large residuals in comparison. This one is smaller, so it's better. Bring us to the last 2 questions. On 24, which residual plot would a linear model be appropriate for the data? Why? Well, residual plot B. If you look at this spread out for the data here, it's fairly sporadic and there's no particular pattern with it, and that would mean that the residuals are random, and that means that a line is a good fit for the data. That's just what happens with the residuals. If the residuals do follow a pattern like on A, so this is answering number 25, we got this like distinct U pattern, and that would mean that the residuals, if you were to graph it, so they start out positive. So here, if I were to draw a line, I would have a bunch of points that are above it, and then I'd have points below it, and then I have points above it again. And this scatter plot would also make a U shape, and that's not a good fit when you're using a line. So a line would not make a good fit for A, the data set that came from A. So there you go.